the letters in a piece of English text, like, say, the beginning of the Wikipedia article about cryptography, again, creative masterminded work here, we'd expect to find a lot more E's, T's, and A's than B's, Z's, and K's. Sure enough, that's exactly what we find. 42 E's and not a single K. The beauty of this approach is that it works even if the letters are scrambled. After all, we're only interested in the frequency of letters, not their positions. So even if we turn our Wikipedia sample into gibberish by rearranging the letters, we still get the exact same result, hinting that this text was originally written in English. In cryptology speak, this method of encryption is known as transposition. A transposition cipher will transpose or move characters around, but otherwise leave them unchanged. It differs from a substitution cipher, which, as the name suggests, can substitute or replace characters. We've already seen an example of this with the Vigenère cipher, where letters are supplanted by new ones according to a Vigenère table. This substitution of letters will often render frequency analysis far less useful, if not outright ineffective. Alright, back to cryptos. What the NSA cryptanalysts did was to simply count all the letters in each row of the crypto ciphertext.
Dude, I'm eating food.
They found
I'm
that
sorry.
15 through 25 produced a frequency count that strongly resembled English. Notice, for instance, how there are plenty of E's and T's, but not a single J nor Z. In other words, this middle portion of cryptos had probably been encoded using a transposition cipher, while the rows above and below had probably been encoded using a substitution cipher. By this point, the NSA team assumed the ciphertext had been divided into 3 segments and felt pretty confident this upper portion was a Vigenère cipher, as Sanborn himself had publicly stated. So the next logical step was to try and suss out the keyword. There are a few different ways to go about this, but a common one is to exploit certain repeating patterns left behind by the encoding process. Remember how in a previous example the keyword hidden was repeated until it matched the length of the plaintext? Well, that repetition can reveal information about the length of the keyword. Imagine we wanted to encode the message ideal concealment of many documents using the keyword mystery. The resulting ciphertext would look like this. Notice how the string EAL becomes WTP both here and here. Likewise, the string MENT becomes DCZR both here and here. This only happens when there's an alignment of letters in both the plaintext and the key stream below. ENS becomes W, ENS becomes W, MNR becomes D, MNR becomes D, and so on. In other words, identical pairings will always produce the same letter. So imagine now that we only had the ciphertext. We'd quickly notice the repetitions of the letters WTP and DCZR. We could then measure the distance between these repetitions.
No, this is
Okay, so there are 7 letters between the beginnings
Caesars.
of these two, and 14 letters between the beginnings of these two.
Crazy bread.
This strongly implies the length of the keyword is 7. And sure enough, the keyword mystery is 7 letters long.